for having me here. I am an adjunct faculty member at the University of Texas at Austin. My specialty is in lithography for micro and nanofabrication. And I'm the editor-in-chief of a peer-reviewed journal on the topic of nanofabrication. A flyer, if anybody works in that area. But in the last 30 years that I've been publishing, I published my first paper 30 years ago. Most of you weren't born when I published my first paper. And I've been the editor-in-chief of a journal for now 3 years. I've learned a lot about publishing and about writing science papers. How many of you have been a co-author or a primary author on a paper that's been published in a peer-reviewed journal? Almost, yeah, more than half. And how many of you were the first author and responsible for writing? Okay. So some of the things I'm going to talk about might have some familiarity with some of the problems and difficulties and things that you've learned from the experience of writing a paper. But I can tell you right now, you haven't learned everything because I am still learning about how to write a good science paper. So I'm going to share with you today some of the things that I've learned that hopefully will make your job easier. First of all, why you need to publish. Well, some of you might be thinking, if I don't publish a couple of papers, my advisor won't let me defend my thesis. Well, that's a pretty good reason. Some of you might be thinking, oh, well, if I want to advance my career or make it in academia, there's a certain publish or perish mentality. And I need to publish in order to get my name out there or establish that I'm a worthy competitor for some job in a faculty position or in industry. That's a pretty good reason. But even if you're not motivated by any of these, what I would call self-centered motivations of what does publishing do for me, there's another reason to publish, and that is publishing scientific works is one of the 3 foundational pillars for science in and of itself. Science cannot exist without a form of communicating scientific results. So let me begin this talk by explaining what science is. Science is really 3 things, 3 legs of a stool, and if any one of these things is missing, science will fall down. It won't be able to support itself. What are the 3 things that you need for science? First, you need a communal collection of knowledge. Some shared sets of facts and theories that we all have available to us that we can use in our scientific pursuits. Then we need a method of evaluating that communal collection of knowledge. In particular, we need a method of evaluating how good our theories are. It generally means taking predictions of our theories and comparing them to experimental realizations, data, and deciding whether one theory is better than another. And finally, we need an attitude of skepticism. You can't just accept any old thing that comes along and say, that sounds good, that must be true. We have to be willing to reject even our most cherished ideas and beliefs that we have learned and grew up being told was true, if we want to consider those ideas scientific. So all 3 of these things make up science: an attitude of skepticism, a method of comparing predictions of theories to experimental data or observations, and a communal collection of knowledge. Scientific publication comes into play in this first one. This first pillar of science requires the ability to preserve and disseminate knowledge. There are lots of different ways of preserving the knowledge that you generate through your activities as a researcher and disseminating that knowledge to others. There are 3 major ones. Textbooks. All of us have learned by reading textbooks and taking classes. Universities are a very important part of collecting up and disseminating knowledge. You also go to conferences. This is a very small conference, but nonetheless, a conference where knowledge is disseminated. We go to scientific talks. It's very, very important to present at a conference the most recent work that you've done and very quickly turn over that knowledge and spread it out to others. But in today's world, the most important way that we preserve and disseminate knowledge is with the scientific journal publication. Until the 20th century, this wasn't true. In fact, the birth of the very first scientific journal was 350 years ago. And before that, it was all letters and books. People wrote letters to each other to express their scientific points, or they wrote books. Books have always and continue to be important. But over time, the scientific journal has become the dominant method of communicating ideas. Can anyone think of a fourth method? I think there's three methods. Taking courses and learning from textbooks, going to a conference and hearing a presentation, and reading a paper in a journal. Anyone think of any other ways in which scientific ideas are disseminated?
Word of mouth or in a community.
That's it, word of mouth. I mean, we are people. I mean, we're not just robots who do science. We're people, and people communicate person to person. And word of mouth. We talk to each other. We're friends. We gain lots of friendships through these conferences and through courses and meetings like this, and we talk. But as a multiplier effect, as a way of taking what you know and the things you might discuss with other people and spreading it out to a larger community, nothing beats the scientific journal. So, at some point in time, you're going to decide that a paper in a peer-reviewed science journal is an important thing for you to do, whether it's important for yourself or whether you decide it's important for science or your field or your community. You will decide that you need to publish. So what does it take? What does it take to do a good job, and what does it take for an editor like myself to decide to accept your work and get it published? There are four things an editor looks for when deciding whether your paper should be accepted or rejected. Let me tell you, if you get a paper rejected, it's okay. It happens to everyone. It's happened to me. It happens. I don't know for sure, but I'm pretty sure Albert Einstein had papers rejected. I mean, not maybe after a couple, after 1905, maybe not, but everybody gets papers rejected. That is not a big deal. But nonetheless, we don't like it. We don't want that to happen. We certainly don't want it to happen frequently. So, we want to make sure that all four of these criterion are met. What are they? Number one, make sure that your paper fits the scope of the journal. There are a few very broad-based journals like Nature and Science, and we all want our papers published in Nature or Science. But for the most part, we will have most of our papers published in journals that are much more specific, that are specialized for a particular topic. Easiest way to get your paper rejected is to send it to the wrong journal. Doesn't matter how good it is, if it doesn't match the scope of the journal, it will be rejected. So, research the scope carefully and figure out which journal to send it to. Maybe the easiest way to think about that is what papers are you reading? What journals are you reading to support your research? Chances are those are the same journals you don't want to be publishing in. Number two, the quality of the paper must be sufficiently high. The quality of the paper has two components: the quality of the research and the quality of the writing. We'll talk about that. We're going to talk about all these in more detail in a minute. Number three, the paper has to be novel. It has to have some novel component. A really, really well-written paper with great research methods that fits the scope of the journal, but has already been published by somebody else, well, it's not going to get published. There has to be something new. And finally, the last thing, the results must be sufficiently significant. That means someone has to care. If you do fabulous work and learn something that nobody cares about, well, why should it get published? All four of these things have to be met. Let's go into a little bit more detail. Scope. You should, like I said, you should pick the journal with the best match of the scope. The idea behind matching the scope of your paper to the scope of the journal is matching the writer with readers. Think of it like a dating game. You're trying to find the people who want to read your paper. The people who are readers, they're trying to find your paper, if they're the ones who want the knowledge that you're presenting. But they can't read every journal out there. They can't survey the entire landscape of what's being published in order to find your result. You need to narrow down the field. You need to make sure that the people who are looking for your work in these journals, those are the journals that you pick to publish. Now, often we use a criterion which is not the optimal criterion. That is, we pick a journal based on how prestigious it is. What's the impact factor? If you don't know what that is, unfortunately, you're going to learn. Impact factor is something to do with how prestigious the journal is, and everyone thinks what I need to do is to publish in a more impactful journal, a higher prestige journal. But if you publish in a journal and it's the wrong audience and everybody who reads it doesn't care, and the people who do care don't read that journal, it doesn't matter. You've made a mistake. You should find the journal with the best scope match. Then if there's a tie, several journals that are equally matched to your scope, pick the one with the highest impact factor, the one that's the most prestigious. That's fine. Novelty, as I said, if your paper does not contribute something unique, something new to the field of science, it's not going to get published in a journal. Now, an exception is the review paper where you're collecting up and reviewing other people's work. That's a different story, but other than review papers, you have to present something novel. What can be new? It could be a new theory, it could be a new method, it could be new materials, or a new tool, new piece of equipment. You could collect new data that's never been collected before, or do some new analysis on data. All of these things are fine. There's lots of ways to do something new. How do you know it's new? Ideally, you've read every single piece of literature in the world that relates to your topic, and so you know. Well, that's kind of hard to do because there's so much that's published. I'll talk about literature searches a little bit later. But you need to effectively search the literature to understand where your work fits. Often, we don't publish a paper for the very first time completely new. Often what we do is we've published, and then we do some more work, and we publish again, then we do some more work, and we publish again. And one of the tough decisions that's kind of hard to judge is when you decide I've got enough new stuff that it's worth publishing a new paper rather than waiting till you're finished. I mean, often some of our research efforts are never finished. There's an infinite amount of stuff we could keep doing, and if we wait until we're done, then we'll never publish. Here's a quick rule of thumb that I like to use when helping people decide whether or not they've got enough new stuff since their last publication to justify a new publication. When you publish something, look at the result. When you are about to submit, rather, look at what you've written down and ask yourself, how much is new? If less than half of what you've written is new, don't publish it. Wait until at least half, more than half of what you're writing is in fact new work, then go ahead and publish it. One of the important things you should do very early when you're beginning to think about writing up your paper is deciding how much is new. How new is it? If you can't clearly explain what is new about your work, compared to the literature, then you're not ready to publish. We'll talk about introductions and cover letters in a minute, but those are two venues that you're going to have to explicitly explain what's new about your paper. Significance. This is the hardest thing to evaluate about a paper. If you're writing up a paper and you think, should I publish this? Is this good enough? Is it significant? Is it important? This is the hardest thing for everybody, but certainly for students to evaluate. What does it mean to be significant? Well, in 2012, there were approximately 28,000 peer-reviewed journals in the world of science. And they published approximately 2 million articles. 2 million peer-reviewed articles published each year. Now, I promise you, a large number of them are just never read. Maybe 1 million of these papers are hardly read by anybody. Now that's a real shame because it takes a lot of work to write up a paper and to get it published. If it's not significant enough that people are willing or interested in reading it, maybe you should think twice about whether or not it's worth your time and effort to actually publish it. How can we judge retrospectively whether a paper was significant? Well, there's no good metric. But the metrics people use are downloads and citations. Now, downloads is kind of a new metric because it's only been the last few years that people have stopped reading papers in the journal printed format. Right? Well, I'm old, I still read the printed format. But nonetheless, even people of my age access the vast majority of the papers that they read online. And so we do have a metric of downloads. How many downloads has your paper received? But in the scientific community, especially the academic community, citations are the metric that most people use. It's an imperfect metric. It's a very imperfect metric of how important your paper is. Nonetheless, it is a metric that we use. I don't think you're going to be able to judge, even in retrospect, in a reasonable way whether your paper is significant. And yet, editors and reviewers are asked to figure that out ahead of time. Right? Before the paper's even been published, let's guess as to how significant it will be. It's very, very hard. One of my complaints about the over-reliance on these metrics of significance, especially citations, is we tend to have a herd mentality, a groupthink. There's a hot topic. You know, everybody's working on graphene transistors. Why? Because everyone's working on graphene transistors. Sure, there's some, we all have some thought that there's some potential there, but once everybody starts working on it, then everyone cites everybody else's work on it, and then if you write a paper on that topic, chances are you'll get a bunch of citations. Whether it's truly significant or not, well, only time will tell. This is the hard one to figure out. The fourth criterion is quality. The quality of research and the quality of writing. I'm about to switch the topic of this talk to be all about the quality of the writing. But before I do that, let's talk about the quality of the research. Hopefully, through both your classes and your experience and the mentorship of your advisor, you're learning something about what it means to do quality research. What are the best known methods, the best processes for performing experiments or developing materials or building tools? What are the best processes for making measurements? What are the best processes for analyzing data? Then we try to, once we know what the best known methods are, we try to use those. Unfortunately, we're always constrained. We're constrained by funds. I would love to buy the latest and greatest spectrophotometer to make my measurements, but what I've got is this old thing that's hanging out in the lab. I have to make do. We have the equipment, the labs, the funds, the people, the time that's available to us, and we do the best that we can given those constraints. The quality of the writing is the real topic that I want to emphasize for the rest of this talk, for a very simple reason. This is the thing that you have the most control over. Now, maybe your advisor has a certain amount of control over how much money gets spent on the lab equipment and how much time you spend making measurements, etc. But chances are you don't have a whole lot of control over quite a few of those things. But what you do have control over is how good the written description of your work is. Given that you've picked a good topic and you've worked hard to do research and do the work required to generate some results, analyze those results, come to some conclusions, the last thing you want is for all that hard work to be wasted because you did a crappy job of writing it up. Right? That is bad. Never give the editor an excuse to reject otherwise good work because of poor writing. Now, here's the important lesson I want to convey to you. You don't have to be a good writer to write a good paper. This is maybe counterintuitive, but in the world of science, it is possible to write a good paper. Maybe not a great paper, maybe not an exceptional paper, but it is possible to write a good paper even if you're not a good writer. That's good because there's a lot of not so good writers in the world of science. Right? We all chose not to become English majors for some reason, right? And one of them is maybe we're not the best writers in the world. But you can still write a good paper if you're a careful writer. And the reason is there is a formula for how to write a good paper. And if you carefully follow this formula, you can do a good job. Now, it's not a formula in the sense of a mathematical formula, and you will always get the right answer if you follow steps A through Z. It's not what I mean. There's a format. That's what I mean by formula. A format, a standard way in which you can go about writing. It's not like a novel where you start with a blank sheet of paper and then anything goes. So what I like to do is talk about the components, the pieces that you can put together in the right way to create a good paper. I have been writing up my thoughts and ideas on the topic of how to be a good science writer for a few years now. And I'd like to promote this web page, which has all of my writings on these topics. And I will spend maybe 1 or 2 slides on each of them coming up in the next 45 minutes. But there's a lot more written in these papers, and I encourage you to read through them. And this is not everything you need to know, but it's what I have to offer so far. The first place to start when you begin to think about how to write down your work is how to structure and organize your paper. If you're writing a novel, some creative writing, then while there are some standard structures available, you basically have a blank slate to do whatever you want. That is not true in science writing. In science writing, we have 2 important goals. And these goals restrict the kinds of organization that we would generally want to use. We want to effectively communicate our ideas. The writing is not an end in of itself. The writing is a tool to do what? To communicate the results of our science, of our research, of our hard work to people who want to know those results. And so what we're trying to do here is effectively communicate. We also want to enable opportunistic reading, and I'll talk about what that is and what that means a little bit later. The easiest way to accomplish this goal is to follow the standard format of a scientific paper. Now, you don't have to do this. This is not a rule you must follow, but about 80% of all scientific papers in the peer-reviewed journal follows a standard format with some variations. And that standard format is called the IMRAD format. Introduction, methods, results in discussion, and then conclusions. With front matter and back matter. So front matter is the title, author list, and abstract. The back matter is the acknowledgments and list of references or citations. But the basic structure of the paper, introduction, methods, results in discussion, conclusion. Let's go through all of those. An introduction. You start a paper with your introduction. The introduction has 3 basic parts. It's a little bit different depending on whether it's an engineering style paper or a science research kind of paper, but it goes something like this. In the engineering world, you explain the topic, the problem you're trying to solve, and then your solution. So you explain all 3 of those things in the introduction. For a more sciencey kind of paper, it might be the topic of the work, your observation or discovery, and then your explanation of that observation or discovery. Another way of describing this introduction, and I like this description a lot, is you begin the introduction by establishing a niche, a territory, rather. You say, this is the area in which my work lies. The reason is very simple. You're trying to match you, the writer, to appropriate readers. And so you have to tell the reader, this is the area of which you're about to read, right? What's the field of the work? Why is this field important? What has already been done? What and so what? What am I doing and why should you care? Another way of thinking about it. Then you establish a niche. What am I doing that's new? Remember, novelty is one of the important 4 criterion for getting published. So tell me what's new. You indicate the gap, you raise a question, you challenge some prior work, you explain something, a problem that needs to be solved. Then you say, I am going to occupy that niche with this new work, this paper. You outline the purpose for your work and how you're going to answer the research questions that you just proposed. Sometimes you might summarize the results here in the introduction, sometimes not. The important thing is you establish a niche and then claim that you are going to fill that niche. So look for all 3 of those things in the introduction. Next comes the method section. Now, method is a very broad word that encompasses a number of things depending on the type of paper that you're writing. The method is how were the results generated. You're going to show some results and then discuss the implications of those results in the next section. But before you show the results, you need to explain how they were generated. If it's an experimental paper, you explain the experimental method. You might talk about the materials that you used. You might develop the theory that you're going to compare to an experiment. You might explain how you design the device that you built, or the equipment that you put together, or the modeling tool that you developed. So how did you generate the results? One of the key features of the method section is that it has to have sufficient detail. And this is a problem that I see in modern scientific literature. We tend to be moving in a direction of minimizing the method sections in our papers. I'm very much opposed to this trend in scientific literature. I'm an old school guy. I think a method section has a very important goal, That is to explain how you generated the results with sufficient detail so that somebody else can evaluate your conclusions. Right? If I don't explain my methods sufficiently, then I can't look at it and say, oh, well, no wonder you got this, because you did this and this. But if you had done that and that, you'd have got something else, and so now I understand. Without sufficient clarity, how can somebody else validate your conclusions? That's the whole goal. Now, it's not that people are going to replicate your work. Almost nobody replicates your work when you publish a paper. If it's sufficiently weird or controversial, maybe somebody will replicate it and show that you're wrong. Hopefully you don't want that to happen. Right? Or if it's sufficiently important, somebody might replicate it in order to modify it and continue to move it or advance it. But the vast majority of papers, nobody ever tries to replicate it. That's okay. That's not really the goal here. The goal here is to make sure that there's enough detail so that someone can nod their head and say, yes, I believe this. I understand and I believe that this is right. Without that detail, people are just going to ignore you. After you explain how you generate the results, you show the results. Usually showing the results is a paragraph. A paragraph plus some tables and graphs. Most of our results are presented in forms of data tables or graphs. And the results in and of themselves occupy a very small amount of the work in that paper. What you do next is you discuss the results. And therefore, results and discussions are almost always combined into the one larger section. Evidence does not explain itself. Once you show the results, you have to explain the significance of that result, those results, to your readers. Otherwise, if you think it may be obvious to you, but I promise you it will not be obvious to the reader. They'll look at it and they'll say, okay, here's a bunch of results, so what? And if you don't explain it, they'll just set it aside and ignore what you did. You need to explain the results and show how these results answer the research questions you posed in the introduction. Remember, you had a niche that you're going to fill, a gap in the knowledge. You pose the research question, and then here is where you say, this is how my results answer that research question. Generally, you flow something like this. You summarize the results, you discuss whether the results were expected or not expected. Both are okay, right? Results are agnostic. Data is agnostic. Whether you expected it or not is something about you, not about the data. So, it doesn't matter either way. Say, this is what I expected, this is not what I expected. Compare the results to previous work. Maybe you have to interpret and explain the results. This usually means comparing to some theory, either saying it confirms the theory or there's something wrong with the theory that needs to be modified. And then, this is also one of the most important things, some kind of hypothesizing about how general these results are. If your results are only specific to your experiment, then chances are nobody's going to care. What you hope to do is have a result which is important, not just for your experiment, for lots of people's experiments. You want to have some guess as to whether or not these results are generalizable. That is, they would affect not just yourself, but other people. And then you end the paper with a conclusion. Conclusions should be short. I see this mistake a lot. People go through a big results and discussion section, and then they have a conclusion, and they just repeat all the same stuff. And they think the conclusion is all that discussion. No, a conclusion is only a couple of paragraphs. You provide a brief summary of the results and discussion. You show how each research question that you pose systematically in the introduction has been addressed. And finally, you explain the significance and the implications of these findings. Now, optionally, you might also add this is where this is going to lead me. Here's some possible ideas for future work. But this should be fairly short. One of the reasons for a conclusion section is called opportunistic reading. I mentioned that earlier. What is that? It would be nice to think that after all that hard work, writing up your paper, that everyone's going to look at it, read the title. Wow, this is exactly what I want to learn about. They read the abstract. Wow, this is fabulous. And then they read every single word in your paper. And of course, immediately you start citing it, everything they do from then on. Right? That's what you hope would happen, but that doesn't happen too often. Think about your own way of reading papers. Do you read every word of every paper? No, you read the title and you decide, that's not interesting to me, or yeah, let me think about it. Then you read a little more, and then chances are, unless it is exactly aligned with what's on your mind that day, chances are you're going to read opportunistically. You're going to read the introduction, maybe the first couple of paragraphs of the introduction, make sure that the paper really is about what you think it is. You're going to skim through what? The figures, right? And you're going to jump to the conclusion. Then, after reading this conclusion, which better only be a couple of paragraphs, which very clearly summarize the results, show how the research questions were addressed, and explain the implications of the work, then the reader will say, I've got everything I need, or let me go and read it in detail because now I'm interested. All right, so that's the structure of the paper. And getting the structure right makes it a lot easier to put together the entire paper. There are a lot of other details you have to pay attention to. And so I'd like to address some of the details now for the next few slides. One detail is authorship. Who gets to be on the author list? This has turned out to be, in the last 10 or 20 years in particular, a very vexing issue in some circumstances. 100 years ago, almost every paper published had one author. But in the 20th century, we started seeing 2-author papers, 3-author papers, 5-author papers, and today, what's the record?
Hundreds.
2,000 authors. I've seen a paper with 2,000 authors.
Or maybe like CERN.
It's like, yeah. So the Higgs boson paper, right? It's going to have everybody who ever worked at the Large Hadron Super Collider listed as an author on that paper. All right, half, because they divided everybody into 2 halves and they're competing with each other. And so, depending on which half you're on, you'll be on one of the 2 papers, right? You know, whether you agree or disagree with that philosophy of assigning authorship, I'm not going to address. I think it's a problem with the physics community. Nonetheless, there are guidelines that I have imposed in my journal that are, I think, pretty universally accepted in most scientific publication about who belongs on a scientific paper. And generally it's not too hard, but every now and then it becomes a conflict, especially because of the publish-or-perish mentality, the idea that people need publications to advance in their careers, and so it becomes personal rather than objective. So let me explain what I think the criterion should be who belongs in a paper. First of all, an author is anyone who has made a creative contribution to the words or ideas being presented that are claimed to be novel. Right. There's a lot in that. That's an important definition. And as a result, I've put together a 3-part test that I think you can easily do. 3-part test for authorship. 1, has the person made a creative contribution to the work? Now, first of all, what is creative? A creative contribution is an intellectual contribution to what is novel. Not everything in your paper is novel. In fact, probably most of what's in your paper is not novel. I made a measurement of a dimension in a scanning electron microscope. Well, unless you invented a new way of measuring in a scanning electron microscope, chances are that is just routine. And so the actual measurement is not a novel part of what you're doing. Think about what's novel and then ask yourself, who made some contribution creatively to this novel content? That can be involvement in the writing. Unless you're plagiarizing, the words are novel, right? So if you wrote the words, you, as an author, you deserve to be listed as an author. Right? But you can be on the author list even if you wrote not a single word, if you were involved in the conception, design, execution, or interpretation of the work. Again, if it was a creative contribution to the novel aspects of the work. So that's the first thing. That should be enough to decide. But there are two more tests that can help you. One is, has the person reviewed and approved the manuscript? If you think, oh, that person over there, you know, I had a lunchtime conversation with them, they gave me a good idea, and I went and tried that out, and sure enough it worked, and so I put it in the paper. Oh yeah, maybe they should be on the paper. But don't just put their name on the paper and submit it without talking to them. Every author needs to review and approve the final submitted manuscript. And with the privilege of being an author on a paper comes responsibility. If you are an author on a paper, then you have to be willing and able to address criticisms that your paper might attract. If somebody attacks your paper, you cannot say, oh, wait a second, they just stuck my name on this, it's not really me, I don't know about that. And you can't beg off. If your name's on there, you have to be willing and able to defend the paper against critics. If you are unwilling or unable to do that, you might think about whether you belong as an author. We have had authorship problems in the scientific community. I have had authorship problems with papers published in my journal. The two kinds of authorship problems, and I have to tell you, much of this comes from the academic community and the pressures of publication in the academic community. But not all of it. There's also commercial problems. So, ghost authors. A ghost author is someone who did work and you left them off. Maybe you left them off by accident. That happens. You simply correct mistakes if that happens. But what sometimes happens is there's somebody who's contributing who wants their contribution hidden. This is usually a corporate sponsor that wants to pretend that their hands are off. So an independent university has validated their device or their product or their drug or whatever. And they want to pretend like they were not involved in the research because people might think the research is biased if their name is on there. We've had problems, especially in the pharmaceutical industries, the medical research industries, where all the work is done by a commercial entity, then they hand it over to a professor who puts their name on it, publishes it, and in fact they didn't do the work. Now hopefully that doesn't really apply too much to what happens in the kind of work that you do. Another problem that might be more typical for you is guest authorship. That is, you add somebody's name on there who really didn't do any work. Why would you do that? Maybe it's because he's your advisor, or she's your advisor. That's a tricky one. It's hard to leave your advisor off if your advisor says to put his name on. Or maybe it's the department chair. Or even in the world of industry, it could be the department manager or section head that always wants his name or her name on the publication. Maybe you want to use some big name. that, you know, happened to visit your lab at some point in time, you had a discussion with them about your work, you say, ooh, I can add their name, and that might improve the chances it'll get accepted. So you just add their big name on there. Knowingly submitting the wrong author list is an ethical violation. It's sufficient reason to reject the paper. It's also, can be, in some circumstances, though not usually, can be sufficient reason to sanction authors. What do I mean? Authors who violate the ethics of publishing, I can sanction them and say, for the next 3 years, I will not accept any paper that you submit to my journal. And I do sanction authors. Usually, the most common reason is plagiarism, but it can be reasons like author violations as well.
Can I ask you, I'm curious, so I know plagiarism exists, but I haven't really seen it practically, anyone ever doing it. Like how, is it, could you give me an example of a time where you caught plagiarism?
I'll give you an example of a paper I'm dealing with right now. It's been submitted. They used the same experimental setup as somebody else. Perfectly fine. Then their data is all new data. But when they described the experimental setup, they used both a figure and an entire paragraph that is word for word out of somebody else's paper. They did not cite that paper. Right? If you take an entire sentence out of somebody else's work and plop it down in your paper, that's plagiarism. That's it. It's one sentence, nothing else. Chances are you'll never get caught. But if you take an entire paragraph word for word, you might get caught. Every paper that goes through my journal goes through a piece of software called Authenticate, which searches the web for the database of all other publications and does comparisons. And, you know, we catch people lifting entire paragraphs, or especially an entire paragraph, and then you also notice the figure is copied. And they don't reference, well, you catch them.
So if say you're using a design, like say someone has a theoretical model and then you're an experimentalist actually trying things out and proving it, I mean, in that case, all you really have to do is cite them, or?
Yes.
Okay.
Yes. Plagiarism is stealing someone's expression,
Okay.
not somebody's ideas. Now, you could steal somebody's ideas, and that's a citation problem. I'm going to talk about citation problems in a minute. If you take someone's ideas and pawn them off as your own ideas, that's a problem. If you take someone's ideas and say, I am taking their idea and trying it out here or there or whatever, well, that's what science is all about. That's what we do in science. We build on other people's work. That is called good science. Right? But if you take someone else's idea and then pretend that you're the one who thought of it, even though you know that you got it from somebody else, that's a problem. That's a citation ethical violation. Now, plagiarism specifically is about the expression. That is the words that you use. You can't take someone else's words. A sort of exception to that is equations. You know, if I use rho to mean density and somebody else has used rho to mean density, well, you know, that's not a bad thing, that's a good thing that we use the same symbols. And once an equation that says, you know, density equals, you know, mass divided by volume, how many different ways are there to write that equation, right? You should, in fact, it's a good thing to write it exactly the same way as other people have written it. It's also a good thing to cite those other people. So you can copy equations exactly as long as you cite them. But you can't copy the words exactly unless you put them in quotes. Even if you take somebody else's words and change them up a little bit, you should still cite. Citing is explaining where you got the idea from. You can't take other people's words no matter what. Yes?
Kind of going back a little bit to guest author, or, well, guest author, I guess would be, is there a percentage, or how much does somebody have to help with the paper in order to be?
There really isn't a percentage. If they have made some intellectual contribution that enhances something novel about the work, even if it's small, that's okay. Right? If it's a small contribution, that's fine. Put them on the author list. I think many people, especially in academia, have the idea that it's better to err on the side of including them than leaving them off. Now, there's some truth to that. But don't carry that kind of, let's be safe and include everybody too far. If it's clear that the person was doing technician work, I don't mean that in any kind of derisive way, but routine work, a routine preparation of a sample, a routine measurement, where there's nothing novel about that, you're not claiming that it's novel, they just helped and did some of the work. They didn't interpret the results. They didn't contribute to what's novel about your paper. Those people belong in the acknowledgement. And they can be acknowledged, profusely. You can say, this work never would have been possible without the efforts of so-and-so who made all these measurements. Right? That's great. But if they didn't contribute to the intellectual content of what's new about your paper, then they belong as an acknowledgement rather than an author. But if they contributed even a little bit, put them in as an author.
So, you mean like if someone is, you come up with something, you give it to a person to do the measurements, but if they interpret the data, so that means that they don't just give you back the raw data, then they will go for the acknowledgement. But if they
No, if they didn't interpret the data, they just collected the numbers and give it